Okay, so good evening. This is the fourth live discussion session, problem solving session for the course Soil Mechanics Geotechnical Engineering 1. In the previous sessions, I've covered and solved some numericals on the basic origin of soil classification, index properties, compaction, seepage, permeability. All these topics have been covered. The videos are available, I think, on YouTube. It's already been uploaded by me. And today is the fourth week, and the topic of today's discussion, problem solving session, is effective stress concept and applications. Effective stress concept and applications. So, like the usual classes, this is a question answer based class. So I'll first of all dictate a set of questions to you. You will need to write down all those questions, either write down or take a screenshot, whatever is feasible for you, whatever you're comfortable with, you can do that. And then after you write down the questions, I will give you some time, around 15 minutes average, to solve those questions. And after 15 minutes, I will start discussing the answers and the explanations behind the solutions. Okay, so this is an interactive session, so I'll ask you the answers. If you can answer, it's fine. If you cannot answer, I'll tell you the answer and give you the explanations for the same. Okay, so like the rest of the classes, this questionnaire also has multiple choice questions. It might have multiple select questions. It might have true false, and definitely it has some numericals. We have to solve. So I will ask you to take your notebook, pen, and calculator also, because there are a set of numericals which you need to solve. I'll give you time, enough time, so that you can solve all the questions, the numericals in that time before I start on with the solution part. Okay. And in case you have any doubts in between, you can stop and ask me. Okay. So this is the fourth week. The topic is effective stress concepts and applications. Okay. So I am going to start with the uh, question dictation part. I will first of all dictate all the questions. Okay. Write down the questions and the options very carefully. All right. Okay. I hope the PPT is visible. Okay. So I'll start with the questions. The first question of this session is, yes, coarse grained soils have relatively low hygroscopic moisture due to their coarse grained soil have relatively low hygroscopic moisture due to their, the options are greater angle of internal friction, limited specific surface, low cohesion, or none of these. All the questions will be with respect to the subject, the topic, effective stress in soils and its applications. Okay, it has effective stress, total stress, pore pressure. So all the questions will be with respect to this particular topic. I repeat the question once. Coarse grained soils have relatively low hygroscopic moisture due to their, the options are greater angle of internal friction, limited specific surface, low cohesion, or none of these. Next question. Almost reversible swelling and shrinkage on re-wetting and re-drying can be observed in soil having high content of. I repeat the question. Almost reversible swelling and shrinkage on re-wetting and re-drying can be observed in soil having high content of. The options are silica, illite, montmorillonite, or kaolinite. I'll repeat the question once. Almost reversible swelling and shrinkage on re-wetting and re-drying can be observed in soil having high content of. The options are silica, illite, montmorillonite, or kaolinite. Okay. Next question. This property offers an explanation for the bulking of sand. This property offers an explanation for the bulking of sand. The options are slaking, high friction angle, activity, or apparent cohesion. I'll repeat the question. This property offers an explanation for the bulking of sand. The options are slaking, high friction angle, activity, or apparent cohesion. Next question. The maximum capillary tension for a tube of 0.05 mm diameter for water at 4 degrees centigrade is. I repeat, the maximum capillary tension for a tube of 0.05 mm diameter for water at 4 degrees centigrade is. All the options are in kilonewton per meter square, and the options are 6.05, 7.03, 6.62, or 7.05. I'll repeat the question. The maximum capillary tension for a tube of 0.05 mm diameter for water at 4 degrees centigrade is. The options are 6.05 kilonewton per meter square, 7.03 kilonewton per meter square, 6.62 kilonewton per meter square, or 7.05 kilonewton per meter square. Write down the data very carefully because this is a numerical. Okay, next question. The pressure transmitted from particles through their points of contact through soil mass is called. The pressure transmitted from particles through their points of contact through soil mass is called. The options are neutral pressure, total pressure, effective pressure, or saturated pressure. I'll repeat the question. The pressure transmitted from particles through their points of contact through soil mass is called. Your options are neutral pressure, total pressure, effective pressure, or saturated pressure. Okay. Next question. Entry of air into the void spaces of clays during drying below shrinkage limit followed by immersion in water causes. I repeat, entry of air into the void spaces of clays during drying below shrinkage limit followed by immersion in water causes. It means that just the clay sample has been dried below the shrinkage limit and then after that, immediately after that, it has been immersed in water. Now what will happen and what is it called? Okay. Your options are swelling, option 2 slaking, third option is shrinking, and fourth option is expansion. Fourth option is expansion. I'll repeat the question. Entry of air into the void spaces of clays during drying below shrinkage limit followed by immersion in water causes. The options are swelling, slaking, shrinking, or expansion. I'll go to the next question. Yes. When the water level in a lake or tank rises, the effective stresses in the soil below. The options are increased, decreased, depends on the particle size, or remains constant. I'll repeat the question. When the water level in a lake or tank rises, the effective stress in the soil below increased, decreased, depends on particle size, or remains constant. Okay, those who are joining now, please write down the questions from the current slide. I'll give you time to solve them and then I'll discuss after that. Okay. Okay, so those who have joined now, just repeat this question. When a water level in a lake or tank rises, the effective stress in the soil below, is it increased or decreased? Depends on the particle size or remains constant. Okay. Next question. The effect of capillary saturation will cause the effective stress to. The effect of capillary saturation will cause the effective stress to. The options are increase, decrease, can be both, or remain constant. I'll repeat the question. The effect of capillary saturation will cause the effective stress to. The options are increase, decrease, can be both, or remain constant. Okay. Next question. Structural water can be removed by oven drying at 55 to 65 degrees centigrade. Is this statement true or false? Whatever the answer may be, you have to come up with the justification behind this. Okay. I'll repeat the question. Structural water can be removed by oven drying at 55 to 65 degrees centigrade. Is this statement true or false? Okay. Next question. In the capillary saturated zone, the pore pressure is. In the capillary saturated zone, the pore pressure is. The options are tensile, compressive, can be both, or zero. I'll repeat the question. In the capillary saturated zone, the pore pressure is. Your options are tensile, compressive, can be both, or zero. Okay. Next question. Water table was found 1 meter below the ground surface. Above the water table, the soil was saturated with capillary water. If the saturated unit weight is 18 kilonewton per meter cube, the effective stress at water table level in kilonewton per meter cube is. The effective stress will be in kilonewton per meter square. Yes, because unit weight multiplied by you know some value will give us that. Okay. So I repeat the question. Please write down the data very carefully. Water table was found 1 meter below the ground surface. Above the water table, the soil was saturated with capillary water. If the saturated unit weight is 18 kilonewton per meter cube, the effective stress at the water table level in kilonewton per meter square is, the options are 8, 9, 18 or 0. I'll repeat the question once. Water table was found 1 meter below the ground surface. Above the water table, the soil was saturated with capillary water. If the saturated unit weight is 18 kilonewton per meter cube, the effective stress at the water table level in kilonewton per meter square is, the options are 8, 9, 18 or 0. Okay. Next question. Hygroscopic moisture can change due to gravity or capillary action only. Hygroscopic moisture can change due to gravity or capillary action only. Is this statement true or false? Those who are joining now, write down the question on the current slide. You'll get time to solve them. Okay. So I'll just repeat the current question. Hygroscopic moisture can change due to gravity or capillary action only. This statement true or false? Next question. Neutral pressure is, what is neutral pressure? I think you have some idea about neutral pressure. Neutral pressure is, option 1, always tensile. Option 2, always compressive. Option 3, compressive below water table and tensile above it. Option 4, compressive above water table and tensile below it. I repeat the question. Neutral pressure is always tensile, always compressive, compressive below water table and tensile above it, compressive above water table and tensile below it. Here you have to definitely consider the capillary reaction, okay, before answering this question. Okay, so next question. I hope it was clear. Take the next question. Yes. The effective stress in kilonewton per meter square at a depth of 10 meter below the ground level when water table is 3 meter below the ground level, saturated density is 20 kilonewton per meter cube is the unit weight and bulk density is 18 kilonewton per meter cube. Okay, write down the data very carefully as a numerical. So we are asked to find out the effective stress at a depth of 10 meter below the ground level. Okay, where water table is below 3 meter the ground level. The soil has a saturated unit weight or density of 20 kilonewton per meter cube and bulk density of 18 kilonewton per meter cube. Okay. In this case, what is the effective stress at a depth of 10 meter? The options are 154, 124, 194 and 144. All the options are in the unit kilonewton per meter square. Okay. I'll repeat the question. The effective stress in kilonewton per meter square at depth of 10 meter below the ground level when water table is 3 meter below the ground level, saturated density is 20 kilonewton per meter cube and bulk density is 18 kilonewton per meter cube is the options are 154, 124, 194 and 144. Okay. Next question. In the capillary fringe, the effective stress is in the capillary fringe, the effective stress is options are less than total stress, greater than total stress, equal to the total stress, or can't be said. So, what is the relationship between effective stress and total stress in the capillary fringe? Okay, so whether the effective stress is more, less, or equal to total stress, or it can't be said. That is, it means it depends upon some other parameters other than just being in the capillary fringe. I'll repeat the question once. In the capillary fringe, the effective stress is, the options are less than the total stress, greater than the total stress, equal to total stress, or it can't be said. Okay. Next question. Softening of soil due to melting of ice is commonly known as softening of soil due to melting of ice is commonly known as? The options are frost heave, bulking, slaking, or frost boil. I repeat the question. Softening of soil due to melting of ice is commonly known as. The options are frost heave, bulking, slaking, or frost boil. Okay. Next question. Another numerical. A river 5 meter deep consists of a sand bed with saturated unit weight of 20 kilonewton per meter cube. Now, gamma W, that is the unit weight of water, is 9.81 kilonewton per meter cube. The effective vertical stress in kilonewton per meter square at 5 meter from the top of sand bed is. So, write down the data very carefully. The river is 5 meter in depth, and the soil, that is the river bed, it is composed of sand, where the sand has unit weight of 20 kilonewton per meter cube. The unit weight of water is 9.81 kilonewton per meter cube. Now, the effective vertical stress in kilonewton per meter square at 5 meter from the top of sand bed. 5 meter from the top of sand bed is. The options are 41, 60, 50, or 51. All the units are in kilonewton per meter square. I'll repeat the question once. A river 5 meter deep consists of sand bed with saturated unit weight of 20 kilonewton per meter cube. Gamma W, that is unit weight of water, is 9.81 kilonewton per meter cube. The effective vertical stress in kilonewton per meter square at 5 meter from the top of sand bed is. The options are 41, 60, 50, or 51. Okay. Next question. Another numerical. The depth of water in a swimming pool is 6 meter. The total and effective stresses in kilonewton per meter square at a depth of 3 meter below the top surface of water is. So here we can see that there is a swimming pool, the depth of which is 6 meter. Now we are asked to find out the total and effective stresses in kilonewton per meter square. Okay, a depth of 3 meter below the top surface of water. So in this question we don't have the value of gamma W given. Okay, gamma W is the unit weight of water. Whenever it is not given, you can assume the value of gamma W as 10 kilonewton per meter cube. Okay, the value of gamma W, you can assume it to be 10. So here you have to assume the value of gamma W as 10 and then solve it. I'll repeat the question once. The depth of water in a swimming pool is 6 meter. The total and effective stresses in kilonewton per meter square at a depth of 3 meter below the top surface of water is. The options are 10, 30, 20, 20, 0, 30 or 30, 0. The first one in the options, the first one is the total stress, and the second one after comma is the effective stress, total and effective stress. Okay. So total and effective stress at depth of 3 meter below the top surface of water. I hope the problem was clear. I'll go to the next question. Yes. A 2 meter thick sand layer of density 1.7 ton per meter cube 1.7 ton per meter cube overlies a 4 meter thick saturated clay of density 2 ton per meter cube of density 2 ton per meter cube. Now, if the water table is at the interface, that is between the sand and clay, at the interface of sand and clay, the effective pressure in ton per meter square at the center of clay layer is. So in this case, we have all the units in ton per meter cube and ton per meter square. Now you should note it down that you should take the density of water to be 1 ton per meter cube. The density of water in this case will be 1 ton per meter cube. Okay, taking that you should solve this problem. So we have a sand layer which is 2 meter thick. The sand has a density of 1.7 ton per meter cube and it overlies, that is, it is at the top of a 4 meter thick saturated clay layer where the clay has a density of 2 ton per meter cube. Now water table is at the interface of the sand and clay layer. We are asked to find out the effective pressure in ton per meter square at the center, mid region, the center of the clay layer. Okay, your options are, all the options are in ton per meter square. The options are 7.4, 5.4, 2.0 or 3.4. I'll repeat the question. A 2 meter thick sand layer of density 1.7 ton per meter cube overlies the 4 meter thick saturated clay of density 2 ton per meter cube. If the water table is at the interface, the effective pressure in ton per meter square at the center of the clay layer is, the options are 7.4, 5.4, 2.0 or 3.4. Okay. Next question. This is the last question, hopefully. Yes. So please draw this diagram, or if you can take a screenshot or a photo of this diagram quickly. So the ground conditions in the site are shown below. So we have a sand which is submerged, that is the water table as the is at the top of the sand layer. Okay, ground level is shown as GL, is the ground level. Okay, so water table is at the ground level. The soil is sand which has the water content or the moisture content of 20%. Specific gravity of soil, that is the G value is 2.7 and the unit weight of water is 10 kilonewton per meter cube. So we have the water table location, the moisture content, the value of G and the value of gamma W. Now we have to find, the first question is the saturated unit weight of sand in kilonewton per meter cube. What is the saturated unit weight of sand? Then we have to find out the total stress, the pore water pressure, and the effective stress. The total stress, the pore water pressure, and the effective stress. Okay. In kilonewton per meter cube at the point P. The point P is shown over here at a depth of 5 meter below the ground level. 5 meter below the ground level, the point P is located. At that point, we to find out the total stress, pore water pressure, and effective stress. Okay. So the given ground condition is water table is at the ground level, the soil is sand, moisture content 20 percentage, specific gravity of solid is 2.7, unit weight of water is 10 kilonewton per meter cube. Now you have to find out the saturated unit weight of sand in kilonewton per meter cube at first, and then to find out the total stress, pore water pressure, and effective stress in kilonewton per meter cube at the point P, that is 5 meter below the ground level. That is 5 meter below the ground level. Okay. So these are the questions. I hope the questions you have, you know, written down the questions. Okay. So I have already dictated all the questions. Okay. I'm giving you, not 15 minutes. I'll give you 13 minutes. I'll start at 7 o'clock. Okay. At 7 o'clock, I'll start discussing. I think someone's mic is on. You can, mute yourself. Yes, thank you. So I'll start discussing the answers from 7 o'clock. You guys can stay in the meeting and solve the questions. I'll start discussing the answers at 7 o'clock. Okay. Have you solved the questions? Anyone? Have you solved the questions? Okay, I'll start discussing the answers now. The PPT is visible, right? Okay. Okay, I'll start. The first question was, Coarse grained soils have relatively low hygroscopic moisture due to their. What is the meaning of hygroscopic moisture? Hygroscopic moisture. Anyone? Has anyone answered this question? Coarse grained soils have low hygroscopic moisture because see, hygroscopic moisture is the moisture content is the water that is being absorbed, okay, on the surface of the soil particles, okay, on the surface of the soil particles. So if we say that a particular soil mass, that particular soil particles, okay, they have greater size. Greater size means in one specific mass, and if the mass is constant, then it will have lesser number of particles. Okay, I have mentioned this in the last class also, I think. So greater mass, larger the particle size, lesser the number of particles. So specific surface is less in the case of coarse grained soils. There is the surface area per unit mass. Surface area per unit mass. Specific surface is less in the case of coarse grained soils because they have lesser number of particles per unit mass. Okay. So when the specific surface is less, then the surface for the moisture to adhere onto becomes less, and hence it results in low hygroscopic moisture. So the answer to this question is limited specific surface. Limited specific surface. Coarse grained soils have relatively low hygroscopic moisture due to the limited specific surface. Okay. I hope it was clear. The explanation. Any doubt regarding this? Okay. Next question. Almost reversible swelling and shrinkage on re-wetting and re-drying can be observed in soil having a high content of. Now these are the clay minerals, mainly silica, illite, montmorillonite and kaolinite. Among these, montmorillonite shows very high degree of swelling and also shrinkage. It is mainly the component found in black soil, because of which it shows swelling and shrinkage. Re-wetting and re-drying means on cycles of wetting and drying, and then again immersing the soil or saturating the soil and drying again. So when it is getting wet, it is swelling, and the swell is almost irreversible at one point of time, and then on re-drying, the soil, it shrinks back. So in the entire cycle, not irreversible, it is reversible. In the entire cycle, if we say the swelling is reversible, it happens during wetting and it shrinks during drying. So this property is due to the mineral called montmorillonite. The mineral called montmorillonite, okay, essential component of black cotton soils, which leads to swelling and shrinkage. Okay. Okay. Next question. This property offers an explanation for the bulking of sand. Any answer? So in sand, what happens is, if we add moisture, this is the volume and this is the water content. So upon the addition of water, the volume increases and then decreases, becomes constant. Now, sand, there are two types, fine grained sand and coarse grained sand. In the case of, you know, fine grained sands, if this is the coarse grained sand, in the case of fine grained sand, we'll see it has gone up. This graph has gone up. Okay, this graph has gone up for sands. What happens is, upon addition of water, there is an increment in volume. Why it happens? Because when the water is added, because it is a coarse grained soil, then there is a capillary action of water. There is a capillary action of water. Capillary action means the pores are interconnected and it leads to a capillary suction. Okay, due to this capillary action, there is an adhesive force between the soil particles. Because of this capillary suction, capillary action, there is an adhesive force between the soil particles, sand particles. And this adhesive force, it seems like there is cohesion in the sand. Although sand particle, that is the sand is a cohesionless soil, it has no cohesion. So this phenomenon is called apparent cohesion. Bulking of sand due to apparent cohesion. That is not the true cohesion. It is the adhesive force between the particles due to the capillary action of water. But it seems that the soil is behaving as a cohesive soil. So bulking happens due to apparent cohesion between the sand particles. Okay. I hope it was clear. Okay, next question. Yes. The maximum capillary tension for a tube of 0.05 mm diameter. Okay. For water at degree 4 degrees centigrade. So at 4 degrees centigrade, we have a formula for the maximum height of capillary water. This is HC max. Maximum height of capillary tension, that is ratio of 0.3084, a constant value, divided by the diameter in centimeter. So now if we put the value, the diameter in centimeter, that is 0.05 millimeter, 0.3084 divided by 0.005. So this is again in centimeter. To convert it into meter, yes, 0.617, almost approximately 0.617 meter. Okay, and here we can take gamma W to be 10, but with 10 there is no solution. We can take gamma W as 9.81. Capillary tension maximum equals to AC max into gamma W. Okay, I should have told you, but anyway, the gamma W value here we should consider as 9.81. Okay, 9.81. So 0.617 into 9.81, getting a value of approximately 6.05. Approximately 6.05. 6.05. What is the unit? Kilonewton per meter square. So the first option, 6.05. Okay. So the maximum capillary tension in this case is equal to 6.05. Okay. Yes. Next question. This is a very easy question. Any answer? The pressure transmitted from particles through their points of contact through soil mass is called. It is called effective pressure. There is a grain to grain transfer of pressure in a soil mass. Okay, neglecting the moisture or water or whatsoever present, only the grain to grain transfer of pressure from the soil mass. to the soil mass. It is called effective pressure. The pressure transmitted from particles to the points of contact through soil mass is called effective pressure. Okay. Now, next question. Entry of air into the void spaces of clays during drying below shrinkage limit followed by immersion in water causes. Now, you have to understand the importance of shrinkage limit. So, if we draw the graph with moisture content on the x-axis and volume of soil mass on the y-axis, then we get a graph like this. Okay, this is the shrinkage limit, this is the liquid limit, this is the plastic limit, and this is the liquid limit beyond which the soil behaves like a liquid. This is the plastic state, this is the semi-solid or stiff state, this is the solid state. Now below shrinkage, this is this part, this particular part below shrinkage limit, even if the moisture is reduced, the volume remains same. So if the moisture is reduced with the same volume, the pores in which moisture was there initially, water was there initially, that will be filled up by air, right? So that is the entry of air into the void spaces of clay during drying below shrinkage limit. Now once we dry it and we bring it to this point where moisture is zero, and then we again immerse that, same clay sample in water, what will happen is it will lead to a creation of very high pressure, because of the re-entry of water in the soil mass. It will create a very high pressure, and it will lead to the disintegration of the soil structure. Okay, disintegration of soil structure. So upon immersion in the water, the pressure becomes very high, which leads to disintegration of the soil structure. Now this phenomenon is called slaking of clays, which is mainly observed in clays only, because in drying, when drying below shrinkage limit, the air enters the void spaces because water is then expelled out, and if it is immersed in water immediately, then what happens? The re-entry of the water in the soil, it creates very high pressure, which disintegrates the structure of the clay mass. Okay, it is called slaking of clay. I hope it is clear. Next question. Yes. When the water level in a lake or tank rises, the effective stresses in the soil below. This is a very easy question, simple question. Okay, water level in the tank or lake rises, the effective stress. Since if the water level rises, we know that there will be no change in the grain to grain transfer of pressure in the soil. That means the effective pressure will remain constant. It is just the pore water pressure or the neutral pressure which is being increasing or decreasing. Okay, so the effective stress upon the rise of water level in a lake or tank, it will always remain constant. Okay, always remain constant. Yes. Next question. The effect of capillary saturation will cause the effective stress too. Now, generally we know that total pressure equals to effective pressure plus pore pressure. The pressure plus pore pressure. When there is capillary saturation or capillary suction, then the pore pressure, it acts upwards, that is the pore pressure is negative. If the pore pressure is negative, then this is minus u, so sigma dash minus u, total stress. Now effective stress will be how much? Effective stress equals to total stress plus u, isn't it? This is the effective stress, sigma effective. This is the total stress, sigma T. This is pore pressure, sigma P. Okay. So in the case of capillary saturation, what happens is the effective stress, it increases. There is water, it will add on to the total stress, effective stress will increase. Okay. So option A is the correct option. Okay. Now next question. Structural water can be removed by oven drying at 55 to 65 degrees centigrade. The statement is false because structural water is a chemically bond water which cannot be removed even if it is boiled till 110 degrees centigrade. Upon boiling at a temperature of more than 110 degrees centigrade, then the bonds break and the chemically bond water can be released, which will lead to a change in the chemical composition of soil mass or anything else. So 50 to 65 degrees centigrade is a very low temperature. It cannot help in removing the structural water. Okay, it is false. Okay, any doubt? Okay, I'll go to the next question. Yes. In the capillary saturated zone, the pore pressure is tensile, compressive. It is a similar question. I'll just draw a diagram and show you. So suppose here is the water table, okay, and this is the base to find out the pressure. So if this is the zone of capillary saturation zone, okay, this is the capillary saturation zone, then here it is compressive, force acting downwards. Here it is the force acting outwards, it is tensile. It is tensile, okay. Here the force is acting upwards, which is negative, as I said, it is also tensile. So in the capillary saturated zone, the pore pressure is definitely tensile, and below the groundwater, the original pore pressure, there is a compressive pore pressure can be observed. So in the capillary zone, the pore pressure is always tensile. Okay. Next question. Water table was found 1 meter below the ground surface. Above the water table, the soil was saturated with capillary water. Now, if the water saturated unit weight is 18 kilonewton per meter cube, the effective stress at water table level in kilonewton per meter square. Okay, so here, if this is the ground surface, 1 meter below this, here is the water table. Now, this is 1 meter. Above the water table, soil was saturated with capillary water. So here, this is the capillary saturation zone. That means the pressure is acting upwards. So in this case, we have gamma sat. We have seen that here in this saturation zone, effective pressure equal to total pressure plus neutral pressure or the pore pressure, right? So in the previous cases where there was no capillary suction, we could have subtracted gamma sat minus gamma w, there is a gamma submerged, and find out the effective stress. But in this case, gamma sat is actually causing the effective pressure because U is acting upwards. So in the case of effective pressure here, what shall we use? Since this is the capillary suction zone, we shall use effective pressure equals to gamma sat into Z, and Z is equals to 1. Z equals to 1. So 18 into 1, that is 18. 18 kilonewton per meter square. So this is the answer. Okay. So I just repeat again, in the capillary suction zone, since effective pressure is the summation of total pressure and the pore pressure, total pressure is the soil pressure, and effective pressure is acting, it is increased because of the capillary suction. So in the case of effective pressure only, we will be using gamma sat, because the saturation that has happened in this zone, it is because of the capillary suction and not the groundwater. Okay, so we will be using this because this is adding on to the effective pressure. Okay, so effective pressure equal to gamma sat into Z, Z equals to 1, gives us 18 kilonewton per meter square. Okay, is it clear? Okay, you are giving the answer. False. Yes, correct. Tensile was correct. 8. No, 8 is not the answer. I think you have given the answer for this question. 8 is not the answer, because effective pressure in this case will not be equals to 18 minus 10. Okay. 18 minus 10, it will be equals to 18, because gamma sat will be taken into consideration. Okay. Next question. Hygroscopic moisture can change due to gravity. Just a moment. Yes. Hygroscopic moisture can change due to gravity or capillary action only. Is it true or false? This is false, because it is the water that has been bonded to the surface of the soil particles. It is due to adhesion or the absorption of water. It cannot change due to gravity or capillary action. Okay, it is a water that has been absorbed on the soil particles. So it is false. Okay. Next question. Neutral pressure is. Neutral pressure is. So neutral pressure, again, as I have shown in this diagram. Okay, I will draw it again once. So this is the soil, this is the water table, this is the point where we want to measure the pressure. So this is the case. This is the capillary suction zone. This is the groundwater. This is the ground level. So it is negative over here and positive over here. Positive means compressive, negative means tensile. So it is compressive below water table and tensile above it. So neutral pressure means the pore pressure, that is U. Pore pressure, it is compressive below water table and tensile above it. Okay. Yes, so this is the slide showing the neutral pressure. It is positive below water table and tensile above it. Okay. Now next question. Yes, effective stress, depth of 10 meter below the ground level. Yes, water table is 3 meter below. So I'll draw it once. Yes, this is 3 meter. This will be 7 meter. So this is total 10 meter. Now this is the water table. Saturated density is 20. So gamma sat equals to 20. Bulk density, that is gamma T. Gamma T equals to 18. So here nothing is said about the capillary suction. Okay. So what shall we do? We shall use the general formula. Effective pressure equals to, first for the first 3 meter layer, that is, now here we have gamma W not given. We will consider gamma W equals to 10. Gamma W equals to 10. Okay. So for the first 3 meter layer, there is no water. It is not saturated. So it will be 18 into 3. gamma total into Z, plus for the second one it will be how much? Gamma sat minus gamma W. This is the gamma submerged into 7. So 54 plus 70, I think it is 124. Yes, 124 kilonewton per meter square. Okay, so I'll just repeat. For the first 3 meter, the gamma T is 18, so it will be 18 into 3. For the next 7 meter, gamma sat is given, it is below the water table, so it will be 20 minus 10, that is gamma sat minus gamma W, gamma submerged into 7. It will give us a value of 124. Okay, 124. Next question. In the capillary fringe, the effective stress in the capillary fringe is more than total stress, because effective stress is, as I mentioned earlier, the same question, total stress plus U, because here U is negative. Okay, U is negative. So effective stress is greater than the total stress. That is the reason in this sum I have used gamma sat for effective stress. Gamma sat for effective stress. If it was total stress, then I would have used in this sum. Can you see in the previous sum? Just a minute. Yes, in this sum I have used gamma sat in effective stress. If it was total stress, then I would have used gamma sat minus gamma W into Z in the case of total stress, because this is the formula for effective stress in the capillary suction zone. Okay, so total stress equals to gamma sigma dash, that is effective stress, minus pore pressure. Okay, I hope it is clear. Yes, effective stress is more than total stress. Next question. Softening of soil due to melting of ice is commonly known as, this phenomenon is called frost boil. Actually, here I am talking about the capillary zone. In the capillary zone, so when the capillary zone, what happens is, when the ice melts, the volume changes and the soil softens. The exactly opposite thing happens when the water in the capillary zone, it freezes. Okay, when the ice, it melts and the water, it freezes, at that time a certain amount of volume change can be observed due to the change in the development of the meniscus. Okay, so when the soil hardens due to freezing, it is called frost heave. Softening of soil due to melting of the ice in the capillary zone, it is called frost boil. Okay, this is, I'm talking about the capillary zone. Okay, in the capillary zone, called frost boil. Okay, next question. A river 5-meter deep consists of a sand bed. Okay, so this is the river. Since this is a river, this is the water table, consists of a sand, it is 5-meter. 5-meter effective vertical space, 5-meter from top of sand bed. 5-meter from top of sand bed. So this is also 5-meter. You have to find it over here in this line. So as we can see, this is the water. So gamma W, and this is saturated. This is sand. This is saturated. Okay, gamma sat. So the effective stress, what shall we do? We will not be counting the top 5-meter, because there is only water, there is no soil. Here we have not mentioned anything about the capillary action. The effective stress at the base will be equals to how much? Will be equals to gamma sat minus gamma W. Gamma sat minus gamma W into Z, that is a 5-meter. Now gamma sat is how much? Gamma sat is 20 given. Gamma W is how much? 9.81 given. Solve it. So it is 20 minus 9.81 into 5, almost 50.95. The value is here given 50.95, approximately equal to 51, the last option. Okay. So we will not be considering the water because I have asked only the effective vertical stress. Okay. Okay. Next question. Yes. The depth of water in a swimming pool is 6 meter. Total and effective stress at a depth of 3 meter below the top surface of water. Okay. So this is the water table. This is the swimming pool. This is water table. Total depth of 6 meter below at a depth of 3 meter. We are asking 3 meter. Okay. Now nothing is mentioned about any kind of soil over here. So soil is not mentioned. There is no grain to grain transfer of pressure. So there is no effective stress. Effective stress is 0. So going by the option, you can see that the only one option has the second part as 0. There is the fourth option. But total stress. Total stress means the entire amount of stress, that is the soil and water combined. There is no soil. So at this level is only water. So I use gamma W. Gamma W not given. You can consider this as 10. So 10 into 3, that is 30. So total stress at 3 meter depth equals to gamma W into 3. Gamma W into 3. 10 into 3, that is 30. So 30 kilonewton per meter square is the total stress at a depth of 3 meter from the top surface of water. And since there is no soil present, there will be no effective stress. It is 0. Sigma dash equals to 0. Sigma at 3 meter is equals to the pore pressure or water pressure. Okay. So 30 and 0. This is the right answer. I hope it was clear. Go to the next question. Yes. 2 meter thick sand layer of density 1.7, what is the 4 meter thick saturated clay of density 2 tons per meter cube. Water table at interface. Effective pressure in ton per meter square at the center of the clay layer is. So first of all, I'll draw the diagram. This is the top of sand layer. It's 2 meter. This is the clay layer. Okay, the clay layer is 4 meter. This is the thickness of the clay layer. This is 2, this is 4, and at the interface is the water table. So this is the water table at the interface. Now sand has a density of 1.7, clay has a density of 2. So sand it is gamma, clay it is gamma sat. Okay. Effective pressure at the center of clay layer, that is at this point. At this point. This point is how much? This distance is 2, obviously. So effective pressure. So first of all, the sand layer, and second is the clay layer. For the sand layer, how much? It will be 1.7 into 2 gamma total, 1.7 gamma total into 2, isn't it? Gamma total into 2. Plus for the clay layer, how much it will be? I have told you gamma W is how much? Gamma W to be taken as 1 ton per meter cube. 1 ton per meter cube is gamma W. So gamma W is 1 ton per meter cube. So I can write over here gamma sat minus gamma W. This is 2. Gamma sat is 2 minus 1 into Z. What is Z? Z is 2. So I can do it here. 1.7 into 2 is 3.4. 3.4 and 2 minus 1, 1 into 2, 2. 3.4 plus 2, it is 5.4. 5.4 ton per meter square. Okay. So the answer is 5.4, the second option. The second option is the answer. So I have done nothing. I have done just computed the pressure of the sand layer and the submerged pressure of the clay layer at the midpoint. Added them both. I found out the answer. Okay. Okay. Next question. This is the last question. Yes. Ground conditions. Okay. So in this sum, it has been given. This is the conditions given. So first of all, the saturated unit weight. We know the formula: saturated unit weight gamma sat. Gamma sat equals to, the formula is G plus S E by 1 plus E into gamma W. Okay, gamma W. Now it has been said that the soil is saturated, sand is saturated. So S equals to 1. What is the value of E? E we can find out. E equals to W, there is the moisture content, into G divided by S. S is again equals to 1. The value of E you can find out. W is moisture content, 20%, it is 0.2. G is 2.7. So 0.2, 0.54. The value of E is 0.54. Putting the value of E over here, that is, what is G? G is 2.7. And gamma W is 10. So the answer is approximately the value of gamma sat. The value of gamma sat in kilonewton per meter cube is, gamma W is 10, 21.04. Okay, 21.04. This is the value of the saturated unit weight. Okay, now we have gamma sat. So you have to find out total stress for water pressure and effective stress. Very easy. So total stress, suppose it is sigma T, it will be equal to gamma sat into 5. What is gamma sat? 21.04. 21.04 into 5 will give us 105.2. 105.2. Okay, and again this value will be in kilonewton per meter square, not cube. Okay, square. Now pore pressure, that is U, how much? Gamma W into 5, obviously. Gamma W into 5, that is how much? 50. 50 kilonewton per meter square. Okay. The last one is effective pressure. Sigma dash equals to total pressure minus pore pressure, because there is no mention of capillary action. So it will be how much? 105.2 minus 50, that is equals to 55.2 kilonewton per meter square. Okay, kilonewton per meter square. I hope it was clear, the solutions. So this is the end of the session. Thank you for attending the class. Meeting has already been completed. The class is officially over. Next class will be held on next week, Monday on 26th, with the next topic of this course, Soil Mechanics, Geotechnical Engineering 1. Thank you.